In this video here, we're going to talk a little bit about magnetic forces on a wire. So in a previous video, we saw an example of the force law of a charge moving in a magnetic field. It involved the cross product, and we had the charge and it has to move and that sort of thing. So as we get started on this idea of the magnetic force on a wire, let's just morph this law around a little bit here and see if we can just get into something that we can actually use to discuss forces on a wire. So this V over here, velocity is always change in position over change in time, like that. So what we can do with this force law right here, something like this. So we're just going to replace V with a delta L over delta T. And now what we can do is we're just going to take this delta P and just slide it over here into the Q. So force here becomes Q over delta T, delta L across B. But now Q over delta T has the units of coulombs per second. That sounds a lot like current to me. So we'll go ahead and make that replacement then. So we can sort of morph this raw magnetic force law, which refers to the magnetic force on an individual charge, into something here that looks more like the something a little more bulk now. We're not talking about a moving charge, we're talking about a whole current, which of course you know is a collection of a lot of moving charges, and there's something about an L and a B in here. And let's go ahead and drop the delta off there because we're just talking about a length here. IL cross B is sort of the one that we're after here. Let's just take a look at how that works. How does IL cross B work for magnetic forces on a wire? Yeah, let's take a look. All right, so we'll rewrite the law up here so we have it handy. Something like that. Okay, so let's look at a couple examples. The first thing we can do here is, of course, what it sort of means then is that, of course, it is a force law, a little bit different one, has a lot of similar properties to the other one here. You do need the B field, of course, and you do need a current. So you need a B field in both laws, and you need a moving charge in the other one, where here's a current here. And what this is right here, sort of a piece of a length of wire right here. So we're talking about in the forces, magnetic forces on a wire. So yes, you actually have to put a wire in a magnetic field to see this, and this will be the length of the wire in the magnetic field. Because you can have a wire like 10 feet long, but if only like 2 inches of it is in a magnetic field, then all 10 feet of it won't contribute to the force. Okay, so in either case, here's an example here, just to get a handle on what's happening here. Suppose we have a big magnet like this, north and the south, and of course what we know is going to happen is the magnetic field lines are going to come out of the south pole and go into the north pole. And be pointed to the right like this. Okay? And so there you go. And so suppose we're doing this here and we have a wire inside this magnet and we draw it so that the current's coming straight out at us. So here's a wire that's been immersed in a field. So the drawings are kind of, I don't know, awful, but just imagine we have this long piece of wire and it's just immersed in this field. So all we see coming at us like this is just the end of the current coming right at us like that. Okay, that's sort of what we're meant to draw here. There's going to be a force on it, and it's IL cross B. So in order to nail this down, I'm just going to use my wooden model right here that we've been using in a few other videos and stuff. So I is the current, can't do anything about that. That's the number of amps that I'm put through the wire. But this is the length of the wire, and the direction of the length of the wire is always in the, this is sort of the magnitude, but the direction of it is always in the direction of the current, for sure. Okay, so it's the length of the wire, but the direction of the wire is the direction of the current's traveling. So in this case here, I have the current coming at me. Okay, so here's what we'll do. It's IL cross B. So my first vector, the A vector right here, I'm going to put that in the direction of the current, which is straight up like this. Here we go, just going to straight up at the camera. There's A. Looks like the magnetic field is over to the right, so it's not going to do to have the B stick sort of pointing this way, so I got to rotate it over like this to get the B vector, or the B portion of my model here in the direction of the magnetic field, and A is going to point up like that. So here's A pointing up. This is the direction of the current. So something like this. And notice this third dimension right here, the C vector, the result of the cross product, is pointing up. So if I put a wire in a magnetic field this way, there's going to be a strong force on the wire, which is going to be up like that. So if you actually did this sort of in a laboratory, maybe you'll see this physics demonstration in class, if you abruptly turn on the current, this wire will actually jump out of the magnetic field. It's a very apparent and very strong force. It's not something that you have to like use a microscope to see or anything like that. So similar thing, suppose I had a wire, but now the current was going in the opposite direction. Well, IL cross B once again. IL is the direction of the current. It's going to be into the page now. Let's put that first A vector into the page like that. I need to put the other vector of my model in the direction of the magnetic field, which is over like this. It looks like that third one, when I orient like this, is pointing down. So the force on this wire is going to be down. This wire will get rejected from the field in a downward sense. And again, very apparent. You do not have to struggle to see this. You can look at, there's some YouTube videos and so on and so forth on it, but I hope you can You can see it sometimes. They're very apparent forces. Okay? How about this one like this? Here's the B field now, straight up. I'm doing this now to get more of the idea that it is a long piece of wire like this. So here's the wire here that's running through the B field. So again, this would be the length of the wire you would count in any calculations because these parts of the wire aren't in the field. So there's the B field like that. Okay? And let's just say that the current's going this way towards the right. I. There's your current like that. Okay? So what do we have? IL cross B. What direction is this wire going to go in? Well, first vector in the direction of the current like that, second vector in the direction of the B field like that, and this third vector like this points straight up at the camera like that. So this wire here, if it was sort of left to persist like this, the force is straight up. There'll be a force like this everywhere along this portion of the wire that's in the magnetic field. This is going to be the force. So this wire here would start to rise up at us like that if it was stuck in a magnetic field like that. So anyway, that's just sort of an application of IL cross B, how it works. So just remember, this is the amount of current. This is the length of wire that's in the magnetic field, and the direction of it is always in the same direction as the current. And of course, you have the direction of the magnetic field right there. Okay? So just to wrap this up then, let's look at another couple cases here. What about if you have two wires next to each other? So suppose I have a wire like this and a wire like this, two currents coming at each other. Sometimes physics books ask for what would the force be on this wire. You're thinking like, well, how can there be a force on this wire? I thought wires can only have forces on them if someone grabs them or they're in a magnetic field. Well, remember, there's a magnetic field produced over here because of this wire. So if I put my right hand in the direction of this one's current and circulate around, there's a big circle of magnetic fields going around this wire, and including that part of the circle that intersects where this other charge is like that. So I draw a big circle like this, like that. It's going to be sort of in this direction, circulating counterclockwise like this. And right here where the wire is, there's going to be a big magnetic field direction straight up like that. B is going to be straight up like that. Okay? So look what I have. I have a wire with a current in it. The wire's coming straight at me in a magnetic field, which is pointing straight up. So I do have a wire in a magnetic field. What's the force going to be? IL cross B. The current, IL, is coming straight towards me, so I get that first vector towards me like that. The magnetic field is straight up like that, going this way. There's my two vectors. And here's that third one right here pointing to the left. So there's going to be a big force on this wire pointing that way. So this wire is going to get pulled towards that one. And we could analyze the problem just the other way. We could focus our attention on this wire, but we'll get the same result. This wire, because of this one's magnetic field, will have a force on it going this way. So two wires that have currents in the same direction are going to sort of attract each other. And again, it's very apparent. Hope you get to see a demonstration of it in class. The two wires are going to suck in and actually touch each other. It's a very strong force, depending on how much current and so on and so forth, but that's just the nature of the game. Wire number 2 can be immersed in wire number 1's magnetic field, and all the magnetic force laws will apply. What about if the wires have currents going in opposite directions, like this and like this? Here's current coming at me, here's current going away from me. Once again, this wire is immersed in this one's magnetic field. Right hand rule, magnetic field is going to circulate around like this. There we go. Something like that. So right here at this point, again, there's an upwards pointing magnetic field. So we have a wire in a magnetic field. Yes, the magnetic field came from another wire, but no one asked where the magnetic field came from. The point is out there's a wire in a magnetic field. What's the direction of the force? IL cross B. I is into the page. B is up like that. So here's I into the page. Here's the direction of the magnetic field straight up. And this is the direction of the force over to the right. So this wire is going to feel a force this way. And we could focus on this wire. Magnetic field into the page. The magnetic field due to this wire is going to circulate around just like that. There'll be a big magnetic field up like that. What direction is it? Force is going to feel? Well, current straight up. Magnetic field going up on top like that. Here's the force, IL cross B. IL cross B, here's the result of the cross product, a force over to the left. So this is B right here, and this is F, and that's F right there. So two wires with currents in opposite directions, the way I've drawn here, you can't quite see this one's current opposite directions, are going to repel each other. The two wires are going to be sitting like this, turn the current on, away they go like that. That's how that will work. So again, this wire is immersed in another wire's magnetic field. So anyway, that's the end of this video here on the magnetic forces. Try to remember that F is IL cross B, comes from QB cross B. It's another cross product. Direction of current, length of wire in the field as a vector, same direction as the current, crossing the magnetic field, And really a lot of the problems are about figuring out what direction will this force be. So there you go. Magnetic forces on a wire.